probability, then we are talking about the everyday discussion that we do about taking chances or making predictions. So probability and likelihood are just similar things, except that likelihood is something talked about by making a guess without any scientific information, and probability is talking about the same guess based on some statistical information that we take from various resources. So we will be talking about probability density, which means that the relative frequency of an event occurring when we repeat the experiment, or the experiment is repeated some other way a number of times. And it should be really a very large number of times to make an accurate estimation of probability. We will talk about decision making based on probability, and it could be exclusive decisions or it could be conditional decision making. So let's go ahead and see how it works. We talk about probability by scientific decisions. Now, what are scientific decisions? Are they simply guesses? We talked just now that they are not simply guesses, they are based on some statistical information. And, excuse me. So the next important thing I want to talk about related to probability is the sample space. The sample space is the collection of all possible outcomes that can occur if we do an experiment. And there could be three types of representations of the sample space. It could be either a list of numbers if the sample space is consisting of simply numbers, then it could be a list, or it could be a tree diagram, and we can talk about a Venn diagram to predict a probability. The Venn diagram would means that we can have two or more than two collectives in which there are some pieces of information, and those pieces of information could be in either one of the collective, or could be sharing between two collectives, or could be sharing between three collectives, all three collectives. So a Venn diagram looks like the one you see in front of you, and you see that the pink circle represents a number of furry animals present in a location. The green one represents the number of flying animals present in a location, and the purple ones represent pets in a certain location. And the way numbers are distributed in this diagram means that all the furry animals could be 0, there could be 1 animal, or there could be 3 animals in different locations. If the information is shared with pets, then there could be no elements. The number 0 represents there could be no elements there that are either furry or a pet. And there could be one element that could be both furry and a pet. And there could be one element that could be a pet or a flying animal, because it comes in the intersection of green and purple circle. Whereas there could be 3 animals alone in the pet section, or it could be 3 animals in both the furry animal section and the pet section. So this is how we interpret information given in a Venn diagram. Another example we normally give when we talk about probability is the example of a coin. Now we know that a coin has two faces. So one face represents generally a head, or sometimes just a crown, that you can see very clearly in the picture, and the other side that represents the number is usually called as tail. So there are two possible outcomes if you toss a coin. It could be either a head or a tail. This is represented in the tree diagram as well on the top of the picture. The number 1 shows the starting point, and number 2 and number 3 show the possible outcomes, where number 2 shows the outcome when it is a head, and number 3 shows the outcome when it is a tail. Such outcomes can also be seen behind me on the board, but it is a more complicated picture, and that stage comes later. Now, we talk about an event when we when we take the chance to measure probability. Then we talk about the existence of an event, or the possible existence of an event. What is an event? It could be a number of outcomes. Now, in the coin example, the event A could be getting at most one head. This is an example of an event. So we can define the event A to be getting at most one head, which means either no head or one head. And the probability of A will be the probability of that event A happening, which is also called the long-term relative frequency, because when we test an event for probability, we just don't test it once. We repeat the experiment again and again as much as we can to get the best results. And it is also very important to note that the probability of event, as I said before, that the chance stays between 0% and 100%. So when we talk about the 0% chance, we talk about the probability to be 0, and when we talk about the 100% chance, we talk about the probability to be 1. So the probability always stays between 0 and 1. Now, what do we mean by saying that the probability of an event A is 0? How do we interpret it in words? It means that there is no chance of the event A to occur. I am sure you understand that. And when we talk about the probability of an event A to be 1, this means that the event A is 100% going to occur. There is no chance of missing it. And if we say that the probability of occurring at event A is 0.5, which means that there is an equal chance of occurring or not occurring, and we call it, we interpret it like there is an equally likely chance of occurring the event of A. Now we go back to the coin example, and we see the head face of a coin here. So we want the probability of the head occurring when we toss a coin. What do you guess? What is the chance that a head will appear? I'm sure you said 50%. You're right. Now let's look at the example of a dice. If you throw a dice, just a single dice, how many faces do you expect to appear? Which means the number of all the possible outcomes that can appear. I'm sure you said 6, because there are 6 faces of a dice. So if I want to measure the probability that a 4 appears, what do you guess? What is the chance of getting a 4 if you throw a dice once? Because there are six faces and 4 can appear only once if you throw the dice once. So the probability of getting a 4 would be 1/6. And now we talk about you sitting in a test in which you have to make a choice of a true or a false answer. How many outcomes do you expect? I'm sure you said 2 outcomes. It could either be true, or false, which means that your answer could be correct or not. So the probability of getting a correct answer would be 1/2. So we can now make the conjecture that the probability of an event to occur depends on 2 numbers, n and s, where n is the number of outcomes of the event A, how many times the event A appears in an outcome, and s will be the total number of outcomes in the sample space. Just like in the previous example, our event A was obtaining a 4 when a dice is thrown in the air, and which means that n would be the number of outcomes when 4 can appear when you roll the dice once, and 4 can appear only once, so n was 1. and S was the total number of outcomes that can appear if you throw the dice, and there were 6 outcomes. So the probability of getting a 4 was 1 by 6, which is n on S. And now we are considering an example of tossing 2 fair coins instead of 1. And when we toss 2 coins, we can expect the outcomes to be appearing in pairs, 1 for each coin. So how many pairs do you expect to be appearing in the sample space S? Of course 4, because there can be 2 heads and 2 tails, and 1 head and 1 tail on each side of the coin. So if we consider A to be the event of having exactly 1 head, then the possible outcomes will be the events that have exactly 1 head. 2 head outcomes will be ignored. So there are only 2 outcomes in the sample space S that represent only 1 head, and that are HT and TH. Now note that they will be considered 2 separate outcomes because they represent the heads and tails from 2 coins, not the 1 coin. So they will be considered 2 separate outcomes. And we see that the number of outcomes in A is 2 and the number of outcomes in S is 4. So our N and S turn out to be 2 and 4, and so the probability of having exactly 1 head comes out to be a half. In the next example is tossing a fair dice. We are considering 1 fair dice, although you can see 2 in the picture. But we are considering tossing a 1 fair dice. It has to be fair. Now these are little details that we need to give importance to. If the dice are not fair, so for example, one face of the dice is very nicely polished and the other is rough, then you will not get accurate results. So it has to be a fair dice, which means it's the same on all sides. So when we toss a fair dice once, then how many outcomes do we expect to appear when it is tossed? Could it be showing 1? Or could it be showing 2? Or could it be showing 5? It can show each of these numbers, right? So how many options are there? There are 6 options. So our sample space S would be the numbers 1, 2, 3, 4, 5, 6. Each of these numbers can appear when we toss a dice once. Okay, now let E be the event that we toss the dice and we get at least 5. What does it mean? If we want at least 5, that which numbers do we want to see? We want to see either 5 or 6. Then that will be fitting our requirement that the number is at least 5. So how many options are there in E? 5 and 6. There are 2 options. So our N turns out to be 2 and S has 6 elements. So we can say that the probability of having the event E, sorry, it's a typo here in A, so it should be E. The probability of having E must be 2 on 6, which is 1 on 3. The event A union B is a special event for an outcome, and that is the event when an outcome is contained in one of the 2 events, at least in one event, either in A or in B. It could occur in both of these events, but we assume that it occurs in at least one event. So we take an example of a set A which has the numbers 1 to 5, and a set B which has the numbers from 4 to 8. And when we talk about the set of A union B, then we are talking about all the numbers that can be either in A or in B or in both, but that should be at least in one of the sets. Then we have to include all the elements of A and B into the set A union B. And if we go back to our example of furry animals, pets, and flying animals, and we are interested in finding the number of animals that are flying or they are pets. Then we talk about the union set of flying union pets. So we'll be talking about the number of elements that are either flying or they are pets. So they could be any of the numbers present in the green or the purple circles. So they could be 0, 1, 3, and 4. And then we talk about the opposite of the union event, that is called the intersection event, A intersection B, for an outcome, which means that we want an outcome to be in both of the events A and B. So you don't have a choice here. Here, the outcome has to be in both the events A and B. And again, we consider the example we considered before of the set A having numbers 1 to 5 and the set B having numbers 4 to 8. And we see that the numbers that are present in both the sets A and B are 4 and 5. And then we go back to our example of our animals, and if we are interested in looking at those number of elements that are flying as well as pets, so they fly as well as they are pets, then we have to look at the animals that are occurring both in the green and the purple section. Now, how many numbers do you see that are common to the green and the purple section? I'm sure you said 0 and 1. Now, you may be confused with the 3 in the pink section, but please note that the pink section is the whole section is not in the intersection of green and purple. Only that part that has 0 is in the intersection of green and purple. Whereas there is a 1 in the mustard section, which is the intersection of green and pink, not in the intersection of 4 and 3 of green and purple, but number 1 is there in the intersection of green and purple, which looks like turquoise here. The next topic of my discussion today is about the conditional probability. And the conditional probability is the probability of an event when it is subject to some condition that another event B has occurred. And we interpret it by saying probability of A given B, which means we are talking about the probability of the event A when some other event B has already occurred. And the formula to calculate probability of A when another event B has occurred is dividing the probability of the intersection of A and B by the probability of B if the probability of B is bigger than 0. Because we know that the probability can be 0 and we don't want to divide any number by 0. So the probability of the denominator must be bigger than 0. Okay, again, back to our animals example. This is a beautiful example that helps us evaluating a lot of things. And we are interested now in evaluating the probability of that the number of elements that are pets, given that they are furry as well. So we will compute the probability of the intersection, those number of animals which are pets as well as furry, divided by the probability of an animal being a furry, the number of animals that are furry only. So the probability of the intersection of pets and furry animals consists of those numbers that lie in the intersection of pets which are green, which are purple, and the furry animals which are pink. And the numbers that lie in the intersection of purple and pink circle are 0 and 3. And the numbers that lie in furry animals are 0, 1, and 3. So we get the probability of pets given that they are furry as 2 on 3. And now there's another interesting example that we are having for tossing one fair dice. We know that there are 6 outcomes in the sample space, and we are now interested in 2 events. Event A is that the face appearing is a 2 or 3, nothing else. And the event B is that the face is even. It's an even number. Okay, what are the possible outcomes for the event A to occur? I'm sure you said 2, because it has to be either 2 or 3, simple. And what are the possible outcomes for the event B to occur? Now, if the event B is an even number from the sample space, then we know that there are only 3 even numbers, 2, 4, and 6. So, the sample space for the outcome A is 2, 3, and that for the outcome B is 2, 4, and 6. And so when we compute the probability of the event A that the face is 2 or 3, given that B has occurred, that the face is an even number, is the intersection of the events A and B. And you can clearly see that the intersection of A and B is just the number 2. And so the probability of A intersection B will be 1, because there is only one number in the intersection, and the probability B will be 3, because there are 3 numbers in the intersection. So the probability of A given B turns out to be 1 on 3.